Hi everyone, today we'll walk through the process of converting telescopic raw data, which is videos, into an image. So we know that we need to record videos from telescopes because one frame might not capture sufficient information due to atmospheric refraction and such problems. And we have many calibration frames as well. I will not be going into that. We'll just be using a very simple example where we have one video and just try to see what processing we can do with the help of code. So obviously, normally we have softwares available like Registax, Photoshop, Inside, etc., etc. But as worshippers of Kennedy Korotkovich, von Neumann, Donald North, and the types, we'll obviously write the code from scratch. Jokes aside, it's mostly to gain a good understanding of how the workings and the algorithms are real. Without much ado, this is just to go to extract the frames or the images from a video that we have. I've just downloaded this data set from this wonderful website which has a lot of open source raw data collected from telescopes. They have given a lot of the information as well about their equipment. This is an amazing setup actually. It is an amazing telescope, and they have provided the colored video. So that's kind of nice for our application. Usually most of the telescopes provide monochromatic channels. It enhances the information that we have, but they've given a colored video, which is great for us. Anyway, so I'm just extracting all the frames out of this. This is just some channel swapping which is necessary because of how OpenCV library works. So it just loads everything in the PGR format and we need to swap it around for RGB format, and I'm just saving that into a NumPy file. So we calculate the maximum across axis 0, which is that in the 500 frames that I had, each of dimensions 480 cross 640 and with 3 channels. In each of the 500 frames that I have, for every pixel value, I will take the maximum value and I will replace it with that for obtaining this image. So this is how I get this image. I just did this operation to understand how much the planet is flickering. Sometimes you have no tracking setups, so your planet might appear to slide across the picture from top to bottom, left to right, or something of the sort. So that requires some sort of correction. Even here you can see that the planet is quite smeared, so we will require some kind of centering and adjusting so that we can neatly stack these 500 frames into one image. Some way we can just combine all the information. So OpenCV provides this wonderful function called bounding rectangle. So it's the tightest possible rectangle that you can fit. So it gives you the coordinates of the top left corner of the bounding rectangle and the width and the height of the rectangle. So there is a slight swap of the axis here. So this represents the y coordinate, this represents the x coordinate, meaning the row and the column accordingly. So on understanding how this CV2.bounding rectangle returns its output, I can just fit a for loop for the 500 frames that I have, and I can simply crop the image along the bounding rectangle. So basically what I have now, after I've cropped an image out like that, is centered images of Saturn. There is no rationale really behind choosing Saturn. Well, Saturn has rings, So after I've cropped the images out, I have 500 images of dimensions 150 cross 350 with 3 channels. So I have managed to center the frames. With my bounding rectangle, I've at least managed to extract my region of interest, which is Saturn in this case, right? So let's plot the minimum, maximum, and mean. So again, the same logic as previously described. I'm taking a pixel, and for all the 500 frames that I have, I'm performing each of these operations for that particular pixel value. And across all the 3 frames, this operation is being repeated. Across all the 3 channels, this operation is being repeated. So maximum shows that sort of consistency in information, right? All the 3 mean and max operations show sort of consistency in the information, which shows that our image has been centered sufficiently. Mean creates the nicest output. I'm guessing it's because of the law of large numbers. So yeah, this is just prettier plotting. One thing or the other is very bad to interpret. Use matplotlib for my purpose. So I'll fly with the mean, of course. You can choose to fly with any one of these. They might create better results, they might not create better results. I don't know, I just chose to go with the mean. So my further processing would be on the basis of that. So now this cell is about extracting the edges and the boundaries, the higher frequency component in the image, basically, where sudden changes are happening. So I'm using this kernel, it's called a Laplacian kernel, and normally when you perform convolution with this kernel on the image, you get the information of contours and edges and textures. So in our case, we will get similar information out of it, right? So, and I define this kernel and I apply the operation cv2.filterDates, performing a convolution internally. So m -1 for the depth and kernel. So what I really have in this variable sharp is the sharpened output. It's just the edges and the textures and the contours that I was talking about. So the operation that I'm going to perform here is called high boost filtering, which is that I'll be trying to boost the high frequency information in our image, namely this edges, contour structures. So this was my image. First one's the image. First or second column is the sharpened output that I have. I mean, when I convolve my image with this kernel, this is the output I have. And now I'm just in these successive frames going to keep adding multiples of this sharp output into our original image. So you can see how the images keep getting crisper successively. So you can see how this is just getting better. You can see the gap between the rings. We can see a fainter set of ring inside, a fainter ring inside. There's a lot more features towards the end, right, as compared to the initial image. So definitely our sharpening operation is paid off well. So I'll be flying with this set of values. I've probably picked some version of that. Yes, I've chosen 15 times sharp. This is a super high value for high boost filtering, but it's obviously giving us good enough results. So once the sharpening and sufficiently crisp image is present, I can just go ahead and perform some kind of histogram equalizations. Histogram equalization is an operation for contrast enhancements, and how it works is we construct a histogram of the image. A histogram is simply a frequency plot of the various pixel intensities that are present in an image, and we construct a cumulative distribution function out of the histogram, and we replace each of the pixel values with the corresponding value in the CDF, the cumulative distribution function, to form contrast enhancement. The idea is that if two similar value pixels have different frequencies of occurrence, then their corresponding contrast values, corresponding pixel values in a transform image have to be as far apart as possible. So it's a global operation, obviously, and I tried to perform it, and it has given a very bad output. You can see that the whites have just blown up a little too much, and it's just not a good image. So this experiment failed. That's okay. I thought maybe we can salvage it with some medium blurring. That option didn't pan out well. Well, no problem. We have no paucity of options. Let's jump to the next alternative. Let's perform CLAHE. It's a contrast limited adaptive histogram equalization. So I'm just tiling it into grids of size 4x4, and in the histogram that I construct, if a certain threshold is exceeded, which threshold is determined by my clip limit, then I will redistribute the exceeded value amongst all the other histogram values present. So say this is my histogram, and let's say this is the part that has been exceeded. I will redistribute this part into all the other values equally. So this process is iterative until all of the values amongst my histograms will not exceed this particular clip limit. So you can see that the green is again out. So I perform another iteration of this, another iteration, until this exceeding problem doesn't happen anymore. So I've applied this same setting of CLAHE. Clip limit 1 has been chosen because that gives the best possible output. I've performed this particular CLAHE on all the 3 channels that I have. CLAHE is performed on 1 channel information. So once I've performed it and I've extracted all of these channels, I have just shaped it back into a picture. And this is the output for CLAHE. That looks pretty good for contrast enhancement. I mean, it went from very little features to a lot more. There's a lot more color variation. There's a lot more information that we can see popping up on the planet's surface. That's nice. But there is still a problem. The image is a little too blue for our taste, right? And there is no significant information in the background. Maybe we can just push it all in the black, and maybe we can just concentrate on our planet, right? So now we can distinguish the image as a background and a foreground. And I want the background to be black. So I can just threshold it on some arbitrarily chosen values. This is an arbitrarily chosen threshold. I can just do a hidden trial, obviously, and that's pretty much how I arrived at these values. So on choosing these values, in my sharpened contrast adjustment has some issues actually. So I actually initially performed this operation on the contrast adjusted image, but we ran into a certain set of errors. I mean, you can obviously see that there's some kind of patches happening on the corners. The overall image is not the best looking. So I thought maybe we can, retrace a step backwards and instead work on the sharpened image, right? So on my sharpened image, I'm performing a thresholding. So I want my background to be black, right? And I want my foreground to just be the thing that I concentrate on when I perform a contrast enhancement operation. So I threshold it here using the NP-where operation. And this is an arbitrarily picked threshold as discussed before. And anything that is below this threshold value goes to 0, 0, 0. And anything above retains its value. So this is how I've managed to extract my planet, or my foreground in this case, right? And now let's apply the contrast enhancement operation on this. Oh, the output looks a lot better than this one, right? I mean, if you notice here, there are certain artifacts occurring on the top right and the bottom left corners. I mean, there's slight discoloration happening there. It doesn't look pretty. So obviously with the background black, this image looks a lot prettier, right? And there's a lot more features that are suddenly popping out. There's a lot more visual contrast that is being achieved here. But the image is still a little to the bluer side of the spectrum. I mean, you can see a lot more bluish tones in the image in general, and that's not a nice thing, right? So let's try to adjust the channel manually. But before that, let's see how the histograms actually look. This should have happened technically right in the front, right on the top when we were loading the images and we managed to stack them together. But well, better late than never. So we can see, as has been obvious, that the reds and the blues are somewhat towards the zeros. I mean, and there are two modes basically. So both of the modes kind of occur around 150 for both the red and the greens. The wider spread mode is around 150, and the smaller mode is around 50, I think, for both reds and greens. For blue though, the entire graph is kind of shifted towards the right, so that's why the image seems to have a lot more tones of blues, which is kind of undesirable right now. I mean, it's not nice in general. I mean, we can clearly see that there's a lot more effect of blue and that's not desired. So you can manually shift the channel backwards by an arbitrary value. And we're obviously performing the clipping operation because it doesn't make sense to have a pixel value of -1 or -3 or -5. So we're clipping any value that goes into the negative range to 0. And anything likewise that crosses 255 is 255. Obviously it won't cross 255 in this operation, but for the sake of completeness we've just provided a value. So yes, on clipping the blue tones in the picture, this is what we get. Again, I decided that such operations should be performed before we apply a contrast enhancement, because again, like we saw in the previous image, any kind of noise or textures that are present in the image are just going to be amplified by a contrast enhancement operation because of the nature of the operation that we apply. So again, we're working on the base sharpened image that we arrived at after the high boost filtering operation, and this is the image with the blue shifts performed. Obviously the image looks a lot duller here, so we can apply the contrast enhancement operation here, and that's it. Maybe there are more steps that can be performed, maybe there are lesser steps possible, I don't know, maybe we could have gone many ways. This has been my experiment so far, and I think it gives us a lot of appreciation for what the software has managed to do under the hoods, you know, with just the buttons being visible, the buttons and sliders. So yeah, I think this is quite close to what we have here in picture. Obviously the image has also been de-rotated to align with the horizontal, but yes, these are my experiments, and this is how in general the whole process of processing an image works. Thank you.